Hello everyone, my name is Nicholas Wiley, and today what we're going to be doing is we're going to be deriving an expression or equation for the heat diffusion through our system using Cartesian coordinates. Now the first thing that we should talk about is the system that we have ahead of us. So what we have is we have some sort of heat that is going to be flowing into the left side of our cube that we have, this controlled specific volume that we have. And then it's going to travel some sort of distance x, which is going to be the length of our side of our cube. And then it's going to be exiting on the right side of our cube. So the first thing that we should talk about is this term right here. It's going to be our heat flow in x plus our differential change in distance x. So our linear change in distance x, I may say. So what we need to do for this is we actually need to do a Taylor series expansion for this right here. And what we're going to do is we're going to use a linear approximation for this. Now, you're saying, why isn't this linear? It looks pretty linear right here. You're just going from left to right. There's a couple other things that we need to consider when talking about this. When we're talking about this system, we may have some sort of energy that could be stored within our cube, or we could also have some energy generated via some sort of exothermic, endothermic reaction that could be inside of here. So due to those outlying factors, we don't know that this is linear, and in fact, it's not. So we need to account for those factors, and we're going to do so via a linear approximation of this. And then also, we're going to go through a couple other equations, factors, that are going to lead us to our final differential equation. So moving along, what we'll do is we'll start with our first term, our Qx, our heat flow in the x direction. What we're going to do is we're going to add the partial derivative of our temperature with respect to our position x, and then we are going to multiply that by our change in our distance x, linear direction x. So this is going to be the first equation that we'll say. I think in the end we may have 4, 5, maybe 6 equations that we're going to go through. But the number one thing that we need to keep in mind while going throughout this, which I'm going to make our second equation, is going to be the energy balance. That is going to be driving our differential equation, canceling different things out so that we're left with a nice equation in the end. So moving along to that, I really hope that I do not smudge this. I tend to smudge it a lot. So we're going to have our energy that is going to be entering our system, which is going to be in the form of our heat flow x in the x direction, Q of x, which we'll get to later. We'll figure out what all the components are, and then we're going to do a little bit of cancellations, a little bit of manipulations. Either way, so we have our energy in, subtracted by our energy that is going to be flowing out. What we're going to also add to that is we're going to be adding our energy generated, which I will denote E subscript G. That is going to be equal to the energy that is stored within our system. As I mentioned before, that's the reason that we couldn't just make this a linear equation. We're going to have some sort of energy generated in here, and then we're also going to have the energy stored within our system. So the next thing I think that we should do is we should try and conquer all of these terms. Now I've already mentioned our energy in, our energy out, so let's move on to our energy generated, which will be equation 3. Now we're going to use our energy that is generated, we're going to use this as a rate. So what we're going to say is our E sub G, dot overhead means the rate of energy that is generated, is going to be equal to our the rate of our heat flow, heat generated in a way. Now when looking at this, we need to figure out our units. So this is going to be in joules per second. And what we have right here is we have something that is going to be in joules per seconds times meters cubed, because this is going to be the heat generated, the rate of our heat generated per volume. So what do we need to do? We're going to need to multiply this by our differential change in volume. Now I'm going to start with that as dV, differential change in our volume. And another quick note that I'm going to make is that the differential change in our volume, when looking over here, is we have dx, our dz, and we have our dy in the vertical position. So we have our dx, our dz, and then our dy. Sorry about that, that was dumb. Dx, dy, dz. And again, this is going to be our differential change in volume terms. So for the rest of the video, I'm going to denote it as our differential change in volume, dV. So now that we have this figured out, we have our energy generated, part of our energy balance figured out. So all we're left with is our energy stored. Now for this, we have a little bit different of an equation. So we have our energy stored, again, it's going to be our rate, going to be equal to rho, the density of our material, multiplied by the heat capacity of our material, and that's also going to be multiplied by the differential change in temperature with our differential change in time. Okay, and yes. Okay, so I feel like I'm forgetting a term, so let's just go ahead. This is going to be kilograms per meters cubed. Shoot. So this is going to be kelvins per second. What we're going to want to do is we're going to want to balance this out so that it gets to those joules per second. Now I'm just trying to make sure I get this right. I believe that's joules over kelvins times kilograms. So our kelvins will cancel out, our kilograms will cancel out. And what are we left with? We have joules over meters cubed seconds. So just like this above, these three terms are going to leave us with another thing that we need to do, which is going to be add our differential volume term. So if you're ever stuck, what I like to do is I like to go through all of the different, all of our different terms right here, figure out the units that they have, balance out the units so that they eventually lead us to this rate of energy that is stored. So we're going to end up with that once we add our meters cubed term, as I've said. So I'll erase that. And this is going to be our equation number 4. It's going to be as follows right here. I'm not sure if I explained that the best, so try and do it a little bit right now. So we have this differential change in our volume. Why did we add this right here? Because when looking at these units right here, what else did we need to cancel out? We needed to cancel out meters cubed on the bottom, or meters cubed, yeah, we needed to cancel out meters cubed, just like we did above here, which is why we multiplied by the differential change in volume. So looking at this now, I think we have every piece that we need. We can start putting things together up in this equation right here. Now, I think what I'm going to do, I'll leave it here for now. We'll make this equation 5, and we're going to be like this. I'll erase this afterwards, just to help with organization, because we're going to have a few more things we need to do as we progress. But either way, let's progress. Energy in, we're going to use our heat flow in the x direction, Q sub x. What we're going to do is we're going to subtract this Q sub x. Plus, now what we're going to do is we're going to change this a little bit. We're going to say the partial derivative with respect to our heat flow in the x direction as it changes with the change in our x position. We're going to do as that changes with dx, of course, as we go from left to right. So that's going to be our energy out term, and we're going to add our energy that is generated within. We're going to say that that is going to be Q dot dV. As I've said, the dV is the dx, dz, dy, all of those terms put together. And then that is going to be equal to our energy stored, which is going to be, try to make sure you guys can see, accidentally rhyming. We're going to have rho multiplied by our heat capacity of our material, so our density of material multiplied by our heat capacity, multiplied by the partial derivative of our temperature with respect to time, multiplied by our differential change in volume. Now what we can go ahead and do is we can do a quick cancellation, and then we're going to apply a law that we know to try and drive this to the end. So first and foremost, what we can do is we can get rid of this qx minus qx. It's very simple. So we're going to be left with a negative here. We have to remember that. And then when looking at all these terms, we pretty much have a pretty solid form that we could use moving forward, but what we're going to do is we're actually going to push this a little further. So what we're going to do is we're going to use this Q of x term right here, and using Fourier's law of heat conduction, which we'll call equation number 6, Fourier's law of heat conduction says that this flow rate, why did I say flow rate? Sorry. Our heat flow in the x direction is going to be equal to our heat flux in the x direction per area multiplied by the area. Now we can break apart this term even further, and he says that this heat flux in the x direction has a certain sort of form that we can use. So we will say that our heat flux in the x direction is going to be equal to the negative k, which is going to take into account this right here, which is going to be the not thermal diffusivity. It's going to be our thermal conductivity, thermal conduction of our material. So negative k, and that is going to be using the partial derivative of temperature with respect to our position, dx. And then what we can also do with that is we can figure out what we're going to need for this area. So we're talking about this face that we have right here. And we're talking about this dx. We're saying as this travels from left to the right face. So that means that this area is going to be the dimension that we have not spoken of, the two dimensions we have not spoken of yet, which is going to be our dz and our dy, as this is going to define that area that this is going to be pushed along in a way, if you'd like to think about pushing it from left to right. This area that we're going to be pushing this along, this area is going to be dz dy. So this can be dz dy. Should have wrote that as dy dz, but we'll fix it down here. So now what we can do is we can actually do a little bit of erasing, and we have this negative out here in front. We also have this negative up here, so that's going to create a positive. So what are we going to be left with? So now that we pulled out that q of x term, what we're going to be left with is we're going to have this partial derivative term right here, and then inside, what are we going to have? We're going to have this term right here multiplied by dy dz. So we're going to have positive k, partial derivative of our temperature with respect to x, and then we're going to multiply by dy dz. And then out here we have this dx term that we had hanging here before. Did not just add that, that was hanging right here, if you remember. So now that we have this right here, this is pretty interesting. First of all, this is going to be our q of x term that we had, right? But what do we have right here? We have dx, dy, dz. And as I made the point a couple times earlier, what does that equal? That is going to equal our dv term. So we can go ahead and do, so we can go ahead and erase this, canceling out this dv term and this dv term. Okay, so this is what we're going to be left with. Now, is there anything else that we can do? For our special circumstance, what we're going to say is that this term right here, the thermal conductivity property of our material, this k value does not change as we move across the distances in any direction along our volume. So what we can do is we can actually pull this k out. I'll just put it right here actually. I'll erase this. So we'll have this k term. That is going to be multiplied by the second partial derivative of our temperature with respect to our position squared, plus our flow q is going to be equal to rho multiplied by, I'm going to run out of room. Sorry, let me make sure I can, okay. So what we have on the left side is the density of our material multiplied by the heat capacity of our material. Then we have our partial derivative of temperature with respect to time. And that is what we're going to be left with. Now for us, what we can do is we can apply another thing that we are going to take even a step further. That is going to be this k term. As I said, this is not going to change with distance. So what we can do is we can multiply everything, or divide everything, multiply by 1 over k, divide by k, however you prefer, over k. And this is what we're going to be left with. Now there's one final step that we have to talk about. That is going to be this term alpha right here, which is going to be the thermal diffusivity. That's a hard word to say. And that is going to be equal to k over rho multiplied by rho, our density of our material, multiplied by the heat capacity of our material. Now the units of this are going to be, I think it's meters squared per second. I believe that is what that's going to be for us. That is going to be our thermal diffusivity of our material. So an important note, what does that mean for us? I can draw a little picture down here. Pretty much what this is going to say, this defines how much energy, or like here, well, it's better if I draw it out and explain it. So let's say that we have a little flame. It's a good flame. We have a flame right here that's burning at 80 degrees Celsius. And we have this bar right here. This is going to be used in our next video. So we have this bar right here. Pretty much what this is going to do is this is going to describe how the heat is diffused throughout this right here. That is what this is going to define, is this system right here. How the heat is going to travel, diffuse throughout, and heat this bar. What is that profile going to look like? So now that we have that in mind, what we can do is we can make one more simple substitution into this. So we're going to be left with the second partial derivative of our temperature with respect to our position, plus the rate of our heat flow over K, rate of our heat flow plus K, sorry. That is going to be equal to 1 over alpha multiplied by our differential partial derivative of temperature with respect to time. So now what we have successfully done is we have derived an equation for the heat diffusion using Cartesian coordinates, and the reason that we only have x is the fact that all of them are going to be the same in this. So you could pretty much just substitute in dz squared, dy squared, and you'd have the same thing. So what I'm doing is I'm just giving you this equation right here. There's no need to write it 2 more times. So this is our final equation. This is going to be very useful in the next part of the video, as I described with this bar right here that is going to be heated by some sort of flame. We're going to check how the heat is going to be diffused throughout this. It may look a little simple, but it's going to be a little bit challenging for us. Either way though, I hope you enjoyed, and this is our final equation, so take notes and get ready for the next video.